Okay, just now we talked about FIR design. Now it's IIR design, nth order IIR. In nth order IIR look like this. Nth order IIR, we have nth order polynomial in denominator and the numerator. That's an nth order IIR. And how do we, so now we have this order n to determine, and then we also have these coefficients in the numerator and the denominator to determine. How do we design these parameters to satisfy the given spec? So that's the problem in IIR filter design. Okay. Have we ever seen filter design in analog? Analog filter design. Are there some names for analog filter design? Okay, so maybe let me ask you another question. Which type of filter design start first? Analog filter design start first or digital filter design start first? Analog or digital? Analog, right? Analog start first, okay. So by the time people start to think about digital filter design, the analog filter design is already very well established. For a given specification, people know how to design analog filter to satisfy the specification. And there are some filter design that's well-known filter design like Butterworth, like Chebyshev, like elliptic filter design. These are all IIR filter design that people know very well. So when they start to think about how to design digital filter, they want to borrow from IIR filter, okay? They want to borrow from analog filter because analog filter people already know how to design it. So they want to use the results in analog filter design to design digital filter. So they would think that maybe somehow if we can transform the analog filter to digital filter, then we can design the digital filter. So different transformations have been proposed to design digital filter, IIR filter. Okay. And one transformation is called bilinear transformation. Bilinear transformation. And the other one is called impulse invariant transformation. Bilinear transformation is the more popular one, and that's the transformation we will talk about today. 就是大概那个时候，大概70年代吧，70年代大家开始设计那个IIR filter 的时候呢，那个 digital 的 IIR filter 的时候呢，那时候 analog 的 filter 呢的 filter 设计呢已经很完整了啊，所以如果给了一个 analog 的 filter 的 specification， 那时候就知道怎么去设计那个 analog filter， 所以呢，大家就想说，那我是不是可以把那个 analog 的 filter 呢，经过一个转换 transformation 转过来变成是 digital filter， 那我就可以直接有那个 digital 的 filter 了啊。所以最重要是在怎么转换。那如果因为我们现在要的 specification 是在 digital domain 的嘛，对不对？所以我现在有一个 digital 的一个 specification。我呢，怎么样可以？因为我要一个转换啊，所以我应该要有一个 analog filter。那个 analog filter， 第一个那个 analog filter 的 specification 应该是什么？那我设计了那个 analog 的 filter 之后，我怎么转换？转换过来之后，这个 digital filter 就会符合我的需求。所以，这个就是我们接着下来想要讨论的哦。那我们在这里讨论的，主要是 bilinear transformation。我们看 bilinear transformation， 它是一个什么样的 transformation？ 那我们应该怎么样去设计那个 analog filter， 去设那个 analog filter 的 specification， 然后经过这个 bilinear transformation 之后，过来的就会是我们要的 filter。Okay, so let's start on bilinear transformation. This is how we transform an analog filter to a digital filter. This HCS is a analog filter, and it's the Laplace transform. And here's how we obtain the digital filter. Okay, we have the Laplace transform, right? And the Laplace transform will be a rational transfer function. We would have like S is A1S and A2S squared, things like that, right? In a rational Laplace transform. And then for each S, we substitute S with this thing. The S is substituted with this form, with this expression, okay? After we do the substitution, it will become a function of Z inverse, right? Become a function of Z inverse. And it's also rational because if you substitute this in, then we still get a rational transfer function, okay? And then that will be our HZ. That's the bilinear transformation. Okay, we say this is the bilinear transformation, right? But we still don't know what kind of transformation it is. So let's look into what kind of transformation it is. Okay. So we have, this is the S-plane, right? In the frequency domain, we would have S-plane and we have Z-plane, right? So this is a mapping of value on the S-plane to the Z-plane. If we have a certain Z0 here, this is a Z0, this is Z-plane, and we have a Z0 here, and the value of HZ at Z0 will correspond to what? Will correspond to Z0, 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 right? So it will correspond to H of HC of S, and S is this thing, 1 minus 0. Some point on the S-plane, right? And what point? Which point on the S-plane? This point. We plug in Z0 into this expression, and then we found out the S somewhere on the S-plane, somewhere on the S-plane. Some S0. Let's call this S0. It's okay? So for every point on the Z-plane, we can find a corresponding point in the S-plane. But what kind of correspondence would we like it to be? Oh well, a rational transfer function, right? So now we can talk about poles and zero. Where would we like the pole and zeros to be? Where would we like the pole, especially the pole, right? Pole, where would we want the poles to be? Somewhere inside the unit circle, right? Somewhere inside the unit circle. We would like the poles to be somewhere inside the unit circle. If we want the poles to be somewhere inside the unit circle, then what kind of mapping? What kind of mapping do we have? What do we like to have here? Because for this continuous filter, this analog filter, we can design it to be stable filter, right? We can design it to be stable filter. But then this HZ is obtained after bilinear transformation. We want the stability to be maintained somehow in this transformation, right? Right. So in the S-plane, on the S-plane, if we have the filter to be stable in causal, where are the poles? Which part of the S-plane should they be? Where are the poles? The left-hand side, right? The pole should be somewhere on the left-hand side. The pole should be somewhere on the left-hand side, okay? So, and the ROC should be this, right? And it should contain the imaginary axis. That's the regional convergence for Laplace transform, right? So, in terms of a Z transform, so what kind of transformation? We would like the mapping to be such that the points on the left-hand plane will be mapped to where? Inside the unit circle. Inside the unit circle. Okay, so that's the kind of transformation we want to have. So there are two things that we want to look at here. First of all, how is the frequency response transformed? Okay, we have this analog filter. It has a certain frequency response. And after the transformation, what is the corresponding frequency response here? That's the first thing. And secondly, we would like to make sure that the transformation that will map the left-hand side plan to the point inside the unit circle. Okay, so let's look at these two things. For the frequency response, we would like to look at when z is equal to j omega, right? So S will be, if we plug in j omega here, we would get 2 times y minus e minus j omega. And let's rearrange this thing so that it will look more agreeable. That let's pull out half the angle here and pull out half the angle at the bottom. And at the top, we would get e j omega over 2 minus e minus j omega half. And the bottom will be just, oh, this one is minus and this one is plus e j omega over 2. Okay. And now we have the face part crossed out. We just have the second part left. And at the numerator, we get 2j sine, right? 2j sine. Sine half omega. Cosine. At the bottom, we get cosine half omega. And we got 2j here and a 2 here. We cross out 2, 2. Then we get just 2j. And then tangent omega over 2. Tangent omega over 2. Wow, what does this mean? When we plug in z equal to e j omega, that means we are looking at some point on the unit circle, right? And the unit circle is where we would like to look at when we look at the frequency response. And omega here, this is omega 0, so this is omega 0, this is ej omega 0. If we look at this point, where does it correspond to? It will be some point. Where is it on the S-plane? Here. So where is this? 2j tangent omega over 2, right? So where is this? S is equal to sigma plus j omega, right? Right? And this is a sigma. And this is omega. Real part and imaginary part. So where is it? It's right on the imaginary axis. Right on the imaginary axis. Okay? Somewhere here. Okay? And what does that mean? What's value on the imaginary axis mean? That's the frequency response of the analog filter. That's the frequency response of the analog filter, right? Remember, on the z-plane, if we just look at this point on the unit circle, the point on the unit circle will correspond to the Fourier transform of the digital filter. And when we look at on the S-plane, which part will represent the Fourier transform of the analog filter? Where on the z-plane, where on the S-plane we can have the Fourier transform? The imaginary axis, right? Imaginary axis, that's where we get the Fourier transform. Okay? So what this means is we look at, if we want to have the frequency response in this bilinear transformation, the point on the unit circle comes exactly from point on the imaginary axis. That's where the frequency response of the analog filter is. Okay? So it's basically the Fourier transform here. That's the analog filter, right? The Fourier transform here would somehow get mapped to Fourier transform on this circle. Okay. So Hej omega will be Hc j 2 tangent omega over 2. Okay. So for example, omega is equal to 0. Then this will be 0. So Hej 0 will be Hc 0. Okay? And for example, HEJ, omega equal to pi over 2, then this will be HEJ pi over 2. This will correspond to HCJ. Pi over 2, plug it in, that will be tangent pi over 4. We get 1, then that will be 2. So HC2J. Okay? And for example, omega is equal to pi, then this is EJ pi. Then we get pi, we plug in pi over 2. Tangent pi over 2 is infinity, right? So we get HCJ infinity. Okay? So from 0 to infinity, it gets mapped to 0 to pi. Okay? This is 0 to infinity, right? This part. It will get mapped to this part. Okay. Now we have this filter. Suppose we have this filter. This is HEJ omega. And how do we get this filter? We get it through the tangent function. Oh, maybe we don't draw this yet. Okay. Let me just have this. If we want to look at the frequency response from here to pi, okay, and there's the tangent function. This is from 0 to pi. Okay. Let me draw it a little bit nicer. Okay. This is from 0 to pi. This is a pi. And tangent function will behave like this. It goes to infinity towards pi. And at pi over 2, the value would be equal to 2. Okay? That's tangent omega over 2. And then 2 times tangent omega over 2. Okay? That's the function, right? And let me draw it. Now you have to look sideways, okay? Suppose this is omega. This is omega. And this is HCJ omega. Okay? And then the filter look like this. That's HCJ omega. Is it okay? You have to kind of look like this to make it right. Okay? The filter look like this. Okay? From 0 to infinity. That's the filter. And then through this mapping, okay, and now we say we want to determine omega 0, the value of omega 0, right? HEJ omega 0 at omega 0. Then we shoot up. We do this mapping. We do this mapping here. And then this value, this will correspond to the value of HEJ omega 0. So the value here would be the value here. And now if we want to know the value at the pi over 2, right here, this is the pi over 2, then we do this mapping and we look at this value and we go up like this. Then this is the value when omega is equal to 2. And at omega equal to pi, this will correspond, shoots up to infinity and then comes back down there. That will be the infinity, omega, a big omega equal to infinity. And we read that value, and that would be the value here. Okay, so now we can map one frequency by frequency, and then we can get a picture for HEJ omega. Okay, so it would look like so. Okay, and now, so that's the frequency response. Right, so indeed, we can have an analog filter, and through this transformation, we will get a low-pass filter, digital low-pass filter. Okay, how about the specification? Specification. How are the specification of the analog filter and the digital filter related? Suppose the spec of hz is omega p, omega s, delta 1, delta 2, how to choose spec for HCS. We determine the corresponding spec for the analog filter, we design the analog filter, and we do the transformation, right? So, how to choose a spec for the analog filter? First thing, how does the ripple size changes? With the ripple size here, the same as the ripple size here. The ripple size is the same. Ripple size of the analog filter the same as the ripple size of the digital filter. They will be the same value, right? They will be the same value. Okay. So for the analog filter, delta 1 and delta 2 should be the same. How about passband edge and stopband edge? If we have a passband edge here, say omega p, this is omega p. If this is omega p, then the correspondingly omega p, that will be 2 times omega p over 2, and then that will be the passband edge of the analog filter, right? So we get 2 times tangent omega p over 2 and 2 times tangent omega s over 2. That will cover it. So from the digital filter, we can determine the spec of the analog filter, and using analog filter design technique, we can design the analog filter, and after that we can apply the transformation to get the digital filter. Okay, so we have the frequency response covered. Now we just need to take care of the stability stuff. Now we know that the mapping of the linear transformation is such that the imaginary axis is mapped to the unit circle. Now we still need to make sure that the left-hand plane is mapped to inside a unit circle, or the inside of a unit circle correspond to points on the left-hand side plane of the S-plane. Okay, so that's the last thing that we need to do. Okay, so let's look at the mapping. We want to look at R. Suppose Z is Rej omega, okay? And we would like to see how, when R is less than 1, that means points inside the unit circle, right? The corresponding point, where are the corresponding point on the S-plane? And S is 2 times Z inverse, right? Where is that mapping? It's right here, okay? Oh, it's right here. The mapping is here. It's like this. So it's actually 2 times Z minus 1 and Z plus 1. Okay, so that's the mapping is, right? So let's plug in this mapping here. Z minus 1, oh, there's 2 times. Oh, this is correct. And then there's 2 times, yes. 1 plus Z minus 1 and Z plus 1. Z minus 1 and then Z plus 1. Okay, so we would like to see where it is. So we would like to pay special attention to the real part of this S value here. Let's try to make the denominator play no role. So let's make it the magnitude of this thing. Okay, we multiply it with its complex conjugate. Then we get Rej omega minus 1. And then the complex conjugate of this thing will be Re minus j omega plus 1. Okay, and we can multiply this out. We get 1 plus Rej omega square, and then we get R square minus 1 plus Rej omega plus Re minus j omega. So this gives us r squared minus 1. Oh, 1 is plus, 1 is minus. This is minus. This is minus, okay? And this one would be 2r sine omega, j. 2jr sine omega, okay? And we are only concerned with the real part, right? Because the real part would determine whether it's on the left-hand side plan or the right-hand side plan. So let's look at the real part. If we just look at the real part, it's this thing. 2 times r squared minus 1, 1 plus r e j omega, then 2 squared. And is it positive or negative? It really depends on r, right? And we see that when r is equal to 1, it's exactly equal to 0, right? And that's consistent with what we have known. When r is equal to 1, that's the unit circle, then it's the point it corresponds to would be the imaginary axis, so the real part is equal to 0. And when r is larger than 1, this value will be larger than 0. And when r is less than 1, it's less than 0. So what this means is that if we are looking at points inside the unit circle, r less than 1, and that will correspond to points on the left-hand side. Alrighty, so perfect. So if we design a analog filter that is stable, so all the poles will be on the left-hand plane, and then after the mapping, the poles will go inside the unit circle, and we still get a stable digital filter. Okay, analog filter, we just mentioned some name, right? Butterworth and Chebyshev, and this is a Butterworth filter. Butterworth filters are always, it's a monotone decreasing magnitude response. And then there's a Chebyshev filter. For Chebyshev, there are 2 types of Chebyshev. Type 1 Chebyshev and type 2 Chebyshev. Type 1 Chebyshev had all the ripples in the passband. Okay, has the ripple in the passband, and after the passband is monotone decreasing. And then there's also type 2 Chebyshev. It has all the ripples in the stopband and the monotone decreasing in the passband. Another one, elliptic filter. Elliptic filter is a using Jacobian elliptic function. And one thing about elliptic filter is just now when we talked about FIR filter design, we talked about equal ripple filter, right? And for just now we look at the Butterworth and the Chebyshev, and we see that they all have part of it that's monotone decreasing. So some doesn't even have ripples, like Butterworth, it doesn't have ripples at all, let alone equal ripple. And Chebyshev, it has some ripples either in the passband or stopband. So in one of the band, it doesn't have ripples at all. But for elliptic filter, it's equal ripple in the passband and stopband. It's equal ripple in the passband and stopband, and it's actually an optimal filter for a given specification. Elliptic design requires the smallest order. Okay. And here is a elliptic filter. Well, it has some ripple in the passband and ripple in the stopband, and it's equal ripple. And now let's use the bilinear transformation to design filter. We use the same specification that we have earlier for Kaiser window and McClellan filter design. We have a 1 minus delta 1, that's a minus 0.3 dB, and delta 2 is minus 50 dB, and the same passband and stopband. And we can use the thing we have just computed, and the passband and stopband edges for the filter is the same as what we had before, and we use 2 times tangent omega over 2 function to compute the passband and stopband edge for the analog filter. Okay, so this is the specification for the continuous time filter, and then we can design the continuous time filter, and then we can apply bilinear transformation to get the desired digital filter. All right, and here's the blow up of the figure in dB. Okay, well, for elliptic filter is very precise, okay, minus 0.3 dB right there in the pass band. And the stop band is exactly at the 50 dB right here. And the all-important order, right? The order that's required to have such a specification, if we use elliptic filter, is equal to 5. That's the order that we need. Okay, remember the order we need for the Kaiser window design? It was 59, right? And for Parks-McLennan, it was a 46. But using IIR filter, elliptic filter design, we only need order equal to 5. Okay, 5th order, elliptic filter. Right, and then let's put all 3 filters together. Oh, here's a comparison. For the same spec, if we use Butterworth, we use Chebyshev, we use elliptic filter design. These are the different filters, okay? For Butterworth, we need order equal to 16 to achieve such a spec. And then Chebyshev, we need order equal to 8. And elliptic is 5. Okay, and IIR filter, we can also use MATLAB to design IIR digital filter. We have, for example, if we want to use elliptic filter, we can use elliptic to estimate the order of the elliptic filter, and then we can use the parameter to design ellip, to use the command ellip to design the elliptic filter. Okay, so here is the plot that has the Kaiser window, has the Parks-McLennan algorithm, and then also the elliptic filter. Okay, all 3 of them together. The blue one is the Kaiser window, green one is the Parks-McLennan, and the red one is elliptic filter. Okay, so that's how they look like in the pass band, and this is what they look like in the stop band. Okay, and this is the elliptic filter, and we can see that elliptic filter, well, the order is much smaller, right? So it doesn't have as many ripples, because 1 dip will correspond to a 0, right? So 0, 0, 0, okay, because it's a 5th order, so it has only 5 zeros, and there's 1 0 at pi. 1 0, and then 1 1 here, but on the other side as well. So the total number of 0 is 5. Okay. So if we compare the FIR and IR design, IR filter design will require fewer order or fewer taps, or it's less complexity in terms of multiplier. But with FIR filter, we can have a linear phase. That's something that we cannot have with the IR filter. And there's also no stability concern. Okay, especially when we really implement the filter, the coefficient will be quantized. Did we talk about coefficient quantization at all? Oh, we did talk about quantizing number, right? Using a certain number of bits, right? Remember when you take samples, then the resolution that you may say that you use 8 bits, you use 16 bits to take the samples, right? And that would cause some error. And when we implement the filter, these coefficients will get quantized. And when the filter gets quantized, the coefficient, the value of the coefficient will be different from what we have designed. And if the original filter may be stable, but after the quantization, the filter may become unstable. Okay, but with FIR filter, there's no such concern at all because there's no stability concern. Okay, and here we also talk something about the number of multipliers that's actually needed in the implementation. Well, for Kaiser window, it's a we say the order is 59, right? So there are actually a total of 60 coefficients, okay? But the Kaiser window, it has, remember the window is symmetric, right? And the ideal low-pass filter is also symmetric. So the filter is actually, is linear phase, Okay, it has a linear phase, generalized linear phase. And it has this symmetry. The coefficients are symmetric. When the coefficients are symmetric, we will talk about, well, actually you're going to watch the video pretty soon. Next week, we are going to talk about implementation. When a filter has a linear phase, we can actually cut the number of multipliers that's needed in half. We only need half as many multipliers using the symmetry. Okay, so the actual number of multipliers that's actually needed is a half, 30. Okay, and similarly for proximal collinear is 23. So if you explore the linear phase property, then the difference between these two looks less dramatic. Okay. Before it was 5 versus fifth order elliptic versus like Kaiser window 60, right? So it's like so many times more number of coefficients. So many the order is so many more times. But if you look at the complexity issue, the elliptic filter, it has the numerator and it has the denominator coefficient. So the total number of coefficients that you need to implement, we will see, well, in the video, is actually equal to 9. And for the Kaiser window, it becomes, because it cut in half, so it's 30. So 9 and 30 is like 3 times, okay? So less dramatic than before.